on 41 through 46 or where that section in there, yeah, the algebra would have really gotten nasty with doing those the long way. And so that was why, again, up on the board I put here the definition, sometimes called the limit definition of the derivative, but it's the definition of the derivative, the formal definition, right? We talked about derivative early on. We defined it as a slope of the tangent line or the instantaneous rate of change, right? So that's kind of an informal definition of the derivative. So this would be the more formal. So really when we use the term definition of the derivative, this is what we're talking about right here. And understand that that means there's two pieces to it. This piece is what? What's this piece? The slope. Come on, we got to know this backwards and forwards. The slope what? Slope of the function. Not at one point. No, not at all points.
Instantaneous rate
Keep talking. I'm not hearing it yet. Keep going.
The definition of f for all x.
No.
No.
So the slope of f between x
and h. And x plus h.
And x plus h. It's
I know he's
okay, yeah, but I heard somebody that 2 points eventually become 1, but that's all of it together. I was only asked about this part, right? So let's go back. Hang on here. We're good. Let me find it.
On the video of this class. All period long. Every time someone asks her
right there.
question, it's like that's out of like 30 seconds.
Okay, on the right hand side, in the red, okay, on the right hand side, you see the definition of the derivative. Now I used a there instead of x, but it's the same thing. X means any point, a means at a single point a, but okay, otherwise and that's what some of you were saying. You were saying at all x. That's true. This is a derivative at all x, but there's two parts to it. You see what I outlined in red. You should know that. If I ask a question on the next quiz of why is this, and I put this definition up here and I ask why is this the derivative, right? That stuff in the red is what you would want to focus in on in your explanation, right? The part I was pointing at is what? The slope between 2 points. What 2 points on the one up here? X and x plus h. Remember that thing I had up there, the sketchpad thing where we could slide, right? And it would move as h went to 0, right? That thing. The 2 points were x and x plus h, right? So it's the slope. That is all that is. That's rise over run. That's all that is. It's subtracting the y's and subtracting the x's. And when we subtract x plus h minus x, we get h, right? So this is simply slope between 2 points. What does this do?
This makes the 2 points become 1.
Which is exactly what we did the very first day of class, right? We wanted to know the slope at 1 second with the door opening. And the way we found it was we picked two really close points, and we picked closer and closer points, and we kept getting the slope at 1, and we could see that it was approaching some value, and that's what a limit is. We're going to talk a lot about that today, about what a limit is. It's what those values are approaching. We can say that h doesn't ever have to get to 0. Now, in the problems we've been doing, the long way ones, eventually we go ahead and put a 0 in for h, don't we? Right? Which is an okay thing to do. But we don't have to be able to do that. Right? We can see what the values of this slope calculation are approaching as h gets closer and closer to 0. Now sometimes in some problems that work out nice, we can eventually just put a 0 in for h and see what it is. But we wouldn't have to. We can see as h gets closer and closer to 0, we can see what these slope values are approaching. We even did that spreadsheet. I think Aaron was the presenter that day. We did that spreadsheet, right? And we could see that those slope values in that column were getting closer and closer to like 2 or something, whatever it was. as we pick the points closer and closer together. That's what a limit is. In that table, in that spreadsheet, we could see those values getting closer and closer and closer. Okay? So that's the definition of the derivative. We can use that kind of like a formula, and that's what these problems were that we were doing here. So you were supposed to do the long way. So on the 1 over x, we start with this function. So what is f of x plus h? Well, we plug an x plus h in for x. So we get 1 over x plus h. Minus f of x, so we get 1 over x. Now, we need to get a common denominator on those. There's 3 algebra things you need to be able to do when you're doing it the long way. Factor and cancel, which is the first one we did, simplest of the 3. There's the bow tie, get a common denominator, and then there's a conjugate. And these 2 that I had you do today are examples of those last 2. So this one's the bow tie thing. So we're going to take x up here, or I just did it like this. I said, well, I'm going to get a common denominator. So take x times x up here, x plus h times the same thing. Okay, if we're bow tying that, then it would just be x up top, x plus h over here. So I got x up top, I got x plus h, and then on the bottom I have x times x plus h. Now I could have distributed that. I could have taken x squared plus hx. That would have been fine. I probably should have just wrote that as one fraction, because that's the whole point of getting a common denominator, is to put it together with one fraction. And then we can't forget that the h is down there on the bottom. So it looks like that. Okay, so now what can we do here? We can subtract. So now remember, this is x minus the quantity x plus h. So this would be x minus h, right? That's very much like the one we had yesterday where we had 2 over x, right? It's almost exactly the same. The x's cancel, and we end up with a negative h there on top. Okay? So we end up with a negative h up there on top, and then we have our bottom here, which is the x plus h. We got an h down here, so we just invert and multiply. Okay? And so that's going to allow us to cancel those h's. See, I mean, that, usually I don't even write that, to be honest with you. I just think of flipping this up here, multiply by the reciprocal, but that counts as that. Makes that a negative 1 up there, and that's the key step. That's the reason we can then put a 0 in for h. And again, a 0 in for h is what's giving the 2 points, or making the 2 points become 1. And that's why now we're not getting the slope between 2 points. We're actually getting the slope out 1 point now, because h becomes 0 and the 2 points become 1. That's how this is working here. Okay, so we cancel those h's. Oops. We cancel those h's, and we end up with that. Now we can put a 0 in for h. So down here we just get x times x, which is 1 over x squared. Now, actually, you said one thing you did was did on the shortcut and then the long way. So this one, now that we've learned the shortcut, now remember the original function here was what? 1 over x? Another way of writing that is, so now that we've learned the shortcut, we know that that derivative actually should be
Negative 2.
which means you would take a negative power, means flip it. So this would actually be negative 1 over, oh,
Boom.
that's nice. They came out the same. That'd be a problem if they did, right? So this gives us f prime. Again, you shouldn't call it the shortcut in the long way. This is by the definition, and that's using the power rule. So that stuff in blue is using the power rule, which we will use to our advantage the rest of the year when we're doing these derivatives, right? Except for this quiz and probably your final and your midterm, where you're going to have to still be able to do things with the definition and recognize the definition and so forth. Okay? Matter of fact, one of the questions that pops up all the time on the final or in the midterm or on the AP test is this question right here. It's on the no calculator part of the test. Now, it's going to seem fairly easy right now, but, well, I don't know how easy it'll feel, but this will be on the no calculator part of the, oops, I did that wrong, not each. But, yeah. So that'll show up on the multiple choice section on the no calculator. And people just freak out because they'll want to do some algebra or some of this conjugate stuff we've been doing, but it's got sine, I can't do that. I can't distribute, that doesn't work, okay? Please don't try to do that. You can't distribute sine because it's not multiplication, so you can't do that. So people will be like, oh my gosh, what do I do? Well, what you're supposed to do is recognize that it's this, right? Look at it, isn't it this? So this really is asking for the derivative, isn't it? It's a derivative of what function?
Sine of x.
Sine. Remember problem 34 and 35 yesterday, where you had to look at something like this and identify the f and the a, right? So what's the f here? Sine of x. Sine of x, right? The pi, this is the a plus h. The a plus h gets plugged in where the x was, right? So the pi has plus h is plugged in where the x was, so that's sine of x. Well, we already know the derivative of sine x. It's what? Cosine of x. And they want f prime at the a value. What's the a value? 5/2. So all this question is asking, what is cosine of pi over 2? And what is that? Cosine of pi over 2 is 0. And it'd be a multiple choice. It would have several options. So this becomes a harder problem, though, a couple months from now when we haven't been working with this a whole lot, right? But that's an example of a problem you'll see where you've got to recognize that that's the definition of derivative. So what they're looking for there is the derivative of the sine function at pi halves. Okay. Anyway, let's go back and do the other one, which is square root of x. Okay. And let's talk about this one. So we've got, here's our function. And so we plug in x plus h into our function. We get square root of x plus h minus f of x, which is square root of x all over h. Now, this is the conjugate scenario, right? We want to do some simplifying to this. Now, the one I just showed you with the sine, there would be no algebra we could do to that. There is some trig identities. You may remember from last year you had a trig identity of sine of a plus b, and you could expand that out. And we could do that with pi halves plus h. And matter of fact, my son who's in Calc 1 at UNK, they had to do that in their Calc 1 class. They had to work with that and use those trig function stuff. We're not going to really do a lot with that, so I apologize if you flunk that next year. But anyway, yeah, you'll be fine. But their professor did allow them to have their trig identities written out or something, so they didn't have to memorize them necessarily. But here's some algebra we can do, right? We need to be able to do this algebra. So we're going to multiply by it's a minus b times a plus b. So we're going to do, we got radical minus a radical. We're going to multiply by radical plus a radical. Okay? So when we do that, here, we get the FOIL here. So when you take this times this, what do you get? X plus h. The outers and inners are going to drop out. That's why you do a conjugate, right? A plus b, a minus b is a squared minus b squared. The outers and inners drop out. This times this is just negative x. So that whole top just becomes x plus h minus x, which is just h. And then the bottom is just this times that, right? So, moving on. So I went ahead and wrote it out, x plus h minus x, so those x's will cancel. And then we got this on the bottom. So now, since the x's cancel, you just have h. Now we can cancel out those h's. And of course, that's the key step, right? Because now we can let the 2 points become 1. Now we can put a 0. Once those cancel out, now we can put a 0 in for h. Okay? And when we put a 0 in for h, this becomes square root of x plus square root of x, which is what? 2 square root of x. Next step. 2 square root of x. So square root of x plus square root of x, we get that. Now, once again, we do have the power rule now. So our original function was square root of x. Another way to write square root of x is x to the 1/2. So according to the power rule, the derivative of x to the 1/2 is to the negative 1/2. Now, we can do a little rewriting of that. Negative power means flip it down to the bottom, so we can go down to the bottom with that 2. So we can have x to the 1/2. Of course, x to the 1/2 is square root of x. So we get 1 over 2 square root of x. So the shortcut matches with what we did it by the definition. Okay? All right. That's probably one of the last ones you'll be assigned to practice before the quiz. So, I mean, you'll have some opportunities, although you're definitely going to get some more practice on the algebra pieces of it. I mean, we're going to talk about limits today, right? A big part of what we're going to do today is investigate the idea of a limit and evaluate the limits algebraically. Well, that's what you just did right there. We just took two limit problems and evaluated them using algebra techniques, okay? The difference is today we're going to start talking about limits that don't necessarily have anything to do with derivatives. It's a little bit of a side trip. Section 2.3 is a little bit of a side trip. We've been focusing on the derivative. We've come up with this definition of the derivative, and really out of nowhere, we picked up this idea of limit. So since a limit is such a key element in the definition of derivative, it's probably a good thing if we spend some time talking about limits. What are limits? Okay, because some of you have been a little confused about that, so we're going to talk about what are limits. Matter of fact, if you looked at the calculus curriculum, the AP calculus curriculum, they talk about three main ideas. There are three main ideas. We've talked about two, the derivative and the integral, and the third one is limits. Because really, calculus doesn't work at all without the idea of limits. Okay, the formal definition of an integral also has limits in it, right? So without limits, the other two don't exist. So we're going to spend some time here talking about limits today. All right, before we do that, let's go ahead and finish up on the homework. I was going to talk about number 46, but if you've got some other ones you want to see, we can do that as well. But on 46, would somebody read me that one? It says f of x is square root of x, take away 3 all over x. Okay, so the only rules we have for finding f prime, and the directions here will find a formula for f prime, right? In most of your homework that you had to do. Find a formula for f prime. So that was using the power, right? So all we really know at this point is derivative of sine is cosine, and we know derivative of e to the x is e to the x itself. And then we know the power. So it's really the only two things we have. So we have no rule for what happens if things are divided. And we talked yesterday about you can't just start picking out powers and doing derivatives, right, wherever they're at. You can't do that. You got to rewrite it. So what can we do to this right here? Okay, I heard both things. There's two ways to think about this. One is you can move this x up to the top as an x to the negative 1, or a 1 over x, and you could distribute it. Okay, and that's a fine way to do it. The other way I heard was split it apart. Now, that's the one I'm going to encourage you to think about because we do see fractions like this a lot throughout the rest of the year, and I just think that's an easier way to do it in some of the things we get to later. So that's the way I'm going to encourage you to think about it. Now, let's talk about splitting apart a fraction. We got to be careful if we do it properly. You can only split apart a fraction if it's got a single denominator. Okay, so a couple of quick examples. You don't have to write these down, but a couple of quick examples. So if we had 3 plus 4 over 7, we know that that's 1, right? That's 7 divided by 7. So I could split that into 3 sevenths plus 4 sevenths, right? As long as I split the top into each of its terms, the top is addition or subtraction, and the bottom's a single denominator, then I could split it apart, and that works fine. But if I have the reverse of that, right? That's also 1. I cannot split apart a denominator. So as long as we make sure we do not do that, right, we cannot split apart a denominator on a fraction. Now, and that seems pretty obvious, but where we get confused is when there's multiplication in there. When there's multiplication, now that's a different story, right? I mean, if I have, it's kind of like having 2x over 3. Well, I can write that as 2/3 times x, right? I could write that as x over 3 times 2, right? You see what I mean? And if it was the other way around, it was 3 over 2x. Well, I could write that as 3 over 2 times 1 over x, right? I mean, when there's multiplication, you can split things apart because what do you do with multiplication and fractions? You just multiply across, right? You just put them together. You just multiply tops, multiply bottom. That's not how it works with adding. And so when we have the addition in there, we've got to, or the subtraction, we've got to be careful. Okay, we've got to be careful not to, split it incorrectly. All right, so anyway, with all that said, this would be, and I'm going to make that a power, so this would be x to the 1/2 over x minus 3 over x, right? Split that apart. Now, what do you do when you have this? Subtract powers. Okay, a lot of times we think canceling, whatever, but I think subtracting powers is a good way because we don't really care about negative powers. We want negative powers. You know, in algebra class, you always want to get away from negative powers. We don't care because we often, like we were showing on 1 over x, we'd rather write that x to the negative 1 so we can do our power. Okay, so 1/2 minus 1 is a negative, so this is x is negative 1/2, and then this x would go up top like that, right? Now notice, it's important that I keep writing f of x here because I have not done a derivative yet. All I've done is algebra, right? I have not changed a thing in this. I just rearranged it, rewritten it. Now I'm ready to do f prime. All right, so what do we get? Negative 1/2 x. Yeah, I want to use improper fractions here, so we took negative 1/2 minus 1, which would be negative 1.5 or negative 3/2, plus positive 3, right?
Yeah.
Negative 1 times negative 3 would be positive 3x. And I'm fine with leaving it like that. You know, I know the old rule in algebra was if you've got radicals in your original problem, probably should go back to radicals in your final problem. And that's not necessary for us. It's not necessary in the AP test, so that's why we do it. Now, it's important you understand that you can, though. Because one of the things we will do, well, let's think about chapter 1. Because eventually we're going to be putting this stuff together here. The chart. If I gave you an f prime graph and then started asking you chart questions, what was the first place you looked on the f prime graph? Didn't you look at where across the x-axis? Isn't that where all the interesting stuff was happening? Right? Your local maxes and your mins and where it was increasing, decreasing. You cared about when f prime was 0, didn't you? Okay? Well, one of the things we're going to get to, not so much now, but in the next quiz, is once we find f prime, we're going to want to set it equal to 0 and solve it. So we would have to take a problem like this and then solve it, right? With the calculator is easy. We'll just tell the calculator to solve it. Without a calculator, those are what we'll have to work on. So we'll have to solve that. So to solve it, we'll have to probably turn them into positive powers, maybe radicals, whatever, and we'll have to do some algebra techniques, right? So you need to be able to do it. But if the question is just find f prime, stop right there. You're good. Okay? All right. Any others that you had questions about in that section? Any of that 18, 17, 20, 44, 40, whatever, any of it. 39. What was the original? What did we go to? 12? Okay. This was 39?
You have to look at like a graph.
Oh, you had to look at the graph?
Yeah.
Okay, let's look at the graph.
It's,
Okay, and what they say? Find the equation of the tangent line. That one? Okay, so, all right, find the equation of tangent line. So let's do it. Y equals m times x minus a plus b, right? And they wanted the tangent line at x equals what? 1. So here's what I'd like for you to start doing with your notation is start doing this. When you get a tangent line problem, just write that right there, right? Because aren't those the two things we need? We need the point at 1, and we need the slope at 1. Well, that's f, and that's f prime, right? So, what's f of 1? So they gave you an f graph, did they?
Yeah.
So the graph they gave you in the example is the f graph, right? And so what does it look like f of 1 is? 5. And then you need f prime. So do you need to just sketch in a slope, or did they tell you? I think they told you in the directions, actually, didn't they?
F prime of 1 equals 4.
Oh, they said right in the directions f prime of 1 was 4. So there you go. Y equals 4, x minus 1, plus 5.
That makes sense.
How's that? Yeah, understand that that's very often the case that the back will say this. But remember, that's just simplifying that. And again, I'm grading it that way because that's how the AP test says they're going to grade, right? They would accept that. So I will. Okay? All right. Let's move on. Let's go ahead and talk about, because we do have a little shorter lesson here today, but that's fine. We'll have time here for what we need to do. But we're going to talk about this idea of a limit. The idea of a limit. Okay? So we're kind of stepping away a little bit from the idea of a derivative now. Okay? So it's kind of like the old rectangle and the square thing. Every square is a rectangle, but not every rectangle is a square, right? Every square is a rectangle, but not every rectangle is a square. Well, that's true here. Every derivative is technically a limit, right? Because a derivative is 2 points getting closer and closer and closer. So every derivative is really a limit problem at its heart. Now we've got these shortcuts so we can do derivatives without doing a limit, but at its core, by definition, every derivative problem is a limit. But not every limit problem has anything to do with derivatives, right? Limits, you can study limits that don't have anything to do with derivatives, okay? So we're just going to study limit problems in general, right? Limit problems in general for a little bit here. So this is how you write a limit. So the limit of a function as x approaches a, let's call that L, whatever that value is. And what it means is the limit, the way you read it, is the limit of f of x as x approaches a is equal to some value L. Now that L is a number. It needs to be a number, right? It's what the outputs, well here, that's what I wrote on the next slide, okay? And I'll get to that in a second. Some of you are copying this down. But it's what the outputs, f of x, right? It's the outputs, the y values. The limit of f of x as x approaches a is equal to L. So it's what the outputs are getting close to, okay? So let me switch to this. So it's what the outputs are getting close to as the inputs get close to some value a, right? It's what the outputs. Now in our derivative example, in our derivative definition, our outputs are slope, right? This thing is slope. So we can think of this as a function on its own, right? This difference quotient, right? That's what 34 and 35 were doing yesterday when they said draw a graph of the difference quotient. We can just think of this as its own function and look at what these values are getting close to. And that's what we did with that spreadsheet. We were looking at those slope values and what they were getting close to. Okay? And they're getting closer and closer to the slope of the tangent line, the slope at that one point. Okay, so that's what a limit is in general. So I just want to do a couple of quick limit problems here. You can just draw real rough sketches if you want to in your notes, it's fine. Or don't draw it, it is okay too. But on the homework today in the book, they're going to give you some pictures and ask you some of these limit problems. We're going to watch a little video here that's kind of, I really like. I think it really helps talk about this idea of a limit. But here would be just a regular old limit problem. Again, forget derivative right now, forget slope, forget all that. Okay? Doesn't have anything to do with those things. Well, don't forget it.
Yeah.
But push it aside a little bit. Okay? So we want to know the limit of x squared plus 1 as x approaches 2. Well, I just graphed x squared plus 1, went over here to 2, which has a value of 5. Doesn't quite line up quite right, but whatever. Has a value of 5 right there. Okay? And what we're saying is that as x gets, I'm going to draw little arrows in here, and you're going to see on the video they use cars, which is kind of a nice way of thinking about it. But what's happening as x is coming in towards 2 from both sides, right? As x approaches 2 from either side, the y values are coming in at what? 5. They're getting closer and closer to 5. As x gets closer and closer to 2, now you might say, well, why don't you just put a 2 in for x? We can. In some limit problems, in the simplest ones, we can go ahead and plug a 2 in. 2 squared plus 1 is 5. That's the answer. Boy, that's easy. Yeah, some of them are. Now, those aren't that interesting, so we won't do a lot of those. I mean, that's, big deal. That doesn't take long. Okay, I like this. Give me a whole quiz full of those. So now let's look at this one. Okay, here's another function. So this would be more like what happened in our derivative example. Here's a function, and you try to plug a 3 into there, what happens? You get 0 divided by 0. What's that? It's undefined. That there is no value. Well, that's kind of what happens to us when we do our slope one, right? If we put a 0 in for h here, we get f of x minus f of x, which is 0, divided by 0, right? So we found out that there actually are values for this. Even though you plug in a 0, it's undefined. When we did a bunch of algebra to it, right, nice things happened. The h's canceled, and we were able to get an answer. Well, here's what's happening here. If we graph this, we can really see what's happening. Now, we also know we could do some algebra here, couldn't we? We could factor this, right? X plus 3, x minus 3, cancel the x minus 3's. And then you just get x plus 3. Now, what is x plus 3 as x approaches 3? Plug a 3 in for x, you get 3 plus 3 is 6. It's kind of like what we were doing here. We worked and we worked and we worked. We got the h's to cancel. Then we could plug a 0 in. We try to plug a 3 in there, we get undefined. But if we do a little algebra to it, get something to cancel, now we can plug the 3 in. We get 6. Now, here's what the graph of that looks like. It looks like the graph x plus 3, which is just a line. But it's got a hole in it, because at 3, that thing does not exist. So everywhere else, it's x plus 3. So everywhere else, it's just a line, except at 3. It's got no value, so it's just got a hole. Now, let me put those 2 blue arrows in. What are those outputs approaching as the inputs are approaching 3? The outputs are approaching 6. Does it matter that there's a hole there? It does not. Because a limit is not about just what is f of 3. If we wanted to know f of 3, we would have just plugged in a 3, right? We just said it's undefined. It is undefined, but the limit is a different question. Closely related, but a different question. The limit is, what are the y values approaching as x gets closer and closer and closer and closer to 3? Well, the y values are getting closer and closer and closer to 6. So we say the limit is 6, even though you can't really ever get there in that graph because there's a hole. Okay, it's a little bit like the doorway. If I told you before you could go to lunch, you had to, wherever you are, you had to stand up and go halfway to the door. And then from there, you had to go half of what was left. And then from there, you had to go half of what was left. You would get really hungry because you could never get there, technically, right? But with a limit, you could. So without limits, you could never eat, right? With a limit, you could actually get to the door because that's the limit. The limit of that sequence, the limit of that is the door, right? Even though technically, if you kept going halfway and then halfway and then halfway and then halfway, technically there will always be a little bit left, right? But the limit, what it's approaching, is the doorway. Okay, that's the idea of a limit. All right. So that's just a brief introduction. Let's take a look at a couple of these little videos that I really like. And whoops.
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit.
Sorry about the buzzing.
In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now, this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot. So we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height. Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at. happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4. There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, negative 2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of negative 2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to negative 2. This begs the question, when exactly does the limit exist? We examine that in the next module.
So when we talk about functions, functions are either defined or they're undefined. So that means it has an output or it doesn't have an output, right? So clearly that function did not have an output at 2. It was undefined at 2. Limits, we say, exist or do not exist. A limit, we're talking about what are the y values approaching, or I like how they say intended. Clearly that graph intended to hit negative 2 there. It just didn't, right? So, but that's okay. The limit is still negative 2. So function being defined and limit existing are closely related, but they're not quite the same. So in that first function, the simple one, the output at 2, where the function was defined at 2, was 4. That was also the limit, because that's what the function was intending to reach at that value. So, right, so they're related ideas, but they're not quite the same. Okay? All right, we're going to go to this next one.
Now you have some idea of what a limit is, and we need to talk about when does a limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x. As long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists.
I like that metaphor. Is that a metaphor? Analogy? I don't know. They meet. You come from both sides. If the graph meets, the limit exists. Okay?
Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However,
even though there's a hole there,
towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right-hand limit of f of x, as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x, as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal.
Okay? So like a piecewise function, right? That would be a great example of where a limit may not exist because they come in, there's that break or something in the graph, right? So the left hand, so that'll be another part of your homework too. You'll see the little negative, that means from the left. The little positive means from the right. So any graph would have a left-hand limit or a right-hand limit. It's the car is going to go somewhere from the left, and the car on the right is going to go somewhere. But the limit only exists, the actual limit, if they meet when they come from those two sides. Okay?
Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrived at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
Okay, so I forgot to mention on that first one where there was a break. Again, I talked about whether the function's defined and the limit existing. They're two different things. So on that piecewise, you had the graph came up and there was a filled-in circle at 4, 1, right? And then there was an open circle up here at 4, 2, and it went like that. So if I ask you on that, what's f of 4, what would you have said? No, I didn't say limit. All I said was f of 4. So if you have this graph, it comes up here, and then it goes like that. And right here is the point 4, 1, and this was 2. If I said, what's f of 4, you would say 1. That's asking, what's the output at 4? The output is 1. What's the limit as x approaches 4? Does not exist, right? Because the limit has to do with the cars meeting. I mean, if we're going to put it in real informal, simple terms, the limit exists if the cars meet. Hole or no hole, doesn't matter. If the cars meet, the limit exists. If the cars don't meet, limit doesn't exist. I mean, that's really it right there. Now, that there's a little bit of technicalities to it, and those kind of things, how we want to write our answers, but the main idea is that. Okay? All right. And then the value of the limit is where they meet, the y value of where they meet, even if there's a hole. Even if there's a hole. Okay, last one of these, and this is going to get into actually doing some calculation using some algebra, and that's what part of our homework is going to be.
Once you can determine whether or not a limit exists, the next logical step is to try to figure out what the heck that limit is. So that's what we'll be focusing on in this section. How do you find a limit? The fancy word for finding the value of a limit is evaluate.
If you have a graph, it's easy, right? I mean, the cars meet. Right? But what if you have an equation?
Numerical answer. There are three major ways to evaluate a limit. They are substitution, factoring, and the conjugate method.
Left off bow tie.
We're going to go ahead and start with the easiest one, which is direct substitution. It is just as easy as it sounds. We'll take an example. Here's one. The limit as x approaches 0 of the fraction x squared minus 1 divided by the quantity 2x plus 3. In order to evaluate this limit, all you've got to do is plug in 0 everywhere you see an x.
That's always the first thing you
So we
try.
put in 0 in the numerator,
Direct
and in the
substitution.
denominator, and we end up getting negative 1 divided by 3. So our limit is negative 1/3. It's as easy as that.
Okay? That's not going to work a lot of the time.
Unfortunately, not all limits are this easy. You've already seen one for which that's the case. Remember that function that we were dealing with in the first section of this chapter? In case you don't, here it is again. The limit as x approaches 2.
So we're going to have problems like this today.
Squared minus 6x.
And the idea is no calculator, so you won't know the graph
minus 2.
stuff like that. The
We
book's
looked
not
at
this.
this before. It had a hole in it at the coordinate 2, negative 2. And we concluded from that the intended height was negative 2, making it the limit. However, it would be nice to be able to figure out why this is true mathematically. And to do that, we'll have to use the factoring method. As you can see, and as we saw before, direct substitution results in 0 divided by 0, which is not allowed. So we'll have to resort to this new method. We'll use the factoring method because the numerator of this fraction is factorable. If we factor it, we'll get x minus 4 times x minus 2. Can you see why that's a good idea? Well, the reason is because now the numerator and the denominator both contain
That's where the 0 over 0 is coming from.
which I'm going to cancel out. This leaves the limit as x approaches 2 of x minus 4. This is much simpler to solve because now you can use substitution. And when I do, I get 2
Just like when we did our problems and the h is canceled, we could plug a 0 in for
Remember,
h.
we knew the limit was going to be negative 2, and we're right. Feels good to be right.
Okay? And then they do a conjugate
If the
example.
substitution method fails and the factoring method fails, you're not without hope. You can still try the conjugate method. Before we talk about the conjugate method, though, we might as well figure out what a conjugate is first. Take a look at this expression. The square root of x minus 4. Now, this is a plain old two-term expression. However, it is easy to make a conjugate. All you do is change the negative sign in the middle to a positive sign. The conjugate of the square root of x minus 4 is the square root of x plus 4. That's all there is to it. Now, what if you see an expression like this in a limit problem? For example, this limit problem. The limit as x approaches 16 of the fraction, the square root of x minus 4 divided by the quantity x minus 16. Well, what we'll do is multiply the top and the bottom of the fraction by the conjugate of the radical expression, which, as we said, was the square root of x plus 4. Now, the magic of this is that as you multiply out, the numerator will actually become x minus 16. You don't want to multiply the denominator out. Leave them as separate factors.
Because you're going to want to cancel,
Since
so
I
you want to
have
leave the
x
bottom
minus
factor.
16 in both the numerator and denominator, I can cancel them, just like I canceled like terms in the factoring method, and I'm left with the limit as x approaches 16 of 1 divided by the square root of x plus 4. Do you see why we didn't want to multiply out the bottom? It makes simplification much easier. Now I'm able to plug in 16. Substitution works. When I do so, I get 1 divided by 8. So the limit as x approaches 16 of my original function is 1/8. And that's the conjugate method.
Okay? One last little bit here.
There you have it. There are three major methods to evaluating a limit. Substitution, which is the easiest. Factoring, which is useful when either the top or the bottom of the fraction is factorable. And the conjugate method, which is useful for radical fractions.
Okay. So, again, emphasize to you that, yes,
So for the factoring method, you know it fails when either you can't factor it or it equals 0. That's when you can't use the factoring method.
well, I would say your first part's right, that it can't factor. I mean, I think it's going to look pretty obvious. You're going to have things like x squared plus 6x minus 8, things that,
Right.
or look like they factor. Something that needs a conjugate method is going to probably have square roots in it. And something that needs the bow tie is going to have, 1 over x minus 1 over 2 over x or something like that. It's going to have a fraction in a fraction. That's where you got to get a conjugate. But the first thing you do is you plug in, just like here, we could plug a 0 in for h, and we would see, oh, we're dividing by 0. So basically what that tells you, when you plug in and get divided by 0, for right now, anyway, that just tells you keep going, right? Do one of these algebra things too. Yes.
Oh, I was just gonna ask, you can't use the substitution method.
Yeah, that's it. That's it. If you plug in any of the examples we do right now, if you plug in a 2 or whatever they were talking about, x approaches 2, x approaches 4, you plug it in and you get a number, go with it. Go with it. That's your answer. You're done. If you get, most of the time you're going to get 0 divided by 0. Most of the time you're going to get 0 divided by 0. And that's going to mean keep going, do your algebra, and hopefully something happens where something cancels, and then plug in, and then you'll get your answer. Right. For right now, that's what's going to happen. Now, something else happens if you plug in and get 6 divided by 0. That's undefined, just like 0 divided by 0 is undefined, but they're two different types of undefined, right? 6 divided by 0 is going to mean something else is going on. We're actually not going to get into that till later, okay? So right now, it's going to be more 0 divided by 0, do your algebra, and then something good should happen, okay? So, I would say on the ones, I would say for right now, if you do get a 6 divided by 0, or a 5 divided by 0 or something like that, then I would put does not exist. I don't remember for sure if that happens here. It might. So, okay, does that make sense? So if you get 6 divided by 0 or 5 or something, some other number divided by 0, then we'll go ahead and say does not exist at this point. Okay? Now later, if we get that, we'll want to investigate a little further. But for right now, that would be the time we would say does not exist. Otherwise, I think what's going to happen on these is you're going to get 0 divided by 0. So do your algebra to it, and you'll come up with a number. And so the other part of the homework is on your assignment sheet, and I'm going to take off a few of those here. So, well, I guess it's the ones I say in class. I had question marks by those, so we're going to not do those. So in the assignment sheet, it says do 1 through 3 and 7 in class. So just maybe we'll do those tomorrow or something in class. So forget, you don't have to do those. So it's just 13 through 26, 39 through 42. Now I will say here that if you would turn to that real quick, I'll show you. Sounds like a lot, but it isn't very much when you look at that 13 through 26. Okay, because what you get there is you get a weird looking graph. Everybody see that graph there on 13? Well, here, I can pull that up real quick, actually. Let me pull that. Does it look like that? Is it that one? No. Something like this one. Actually, this is on 27 through 36. But so you get a graph like this, okay? Well, do you see how all the different questions and they're going to ask you? And so they'll ask you something like this. The limit as x approaches, let's just do one here. The limit as x approaches 1 on this graph. The limit as x approaches 1. Think about the cars. Where do the cars meet? At -2, right? This car and this car, as x approaches 1, are going to meet at -2. That's the intended height of that function. Now, is that the actual value at 1? No, but that's the limit. What is the limit as x approaches -1? Does not exist. The two cars do not meet. Does not exist, right? Now they might ask you just what's the f value? What's the f value at -1? What's the f value of -1? 2, right? But the limit as x, and then they might ask you from the left and from the right. From the left as x approaches -1, what's the limit? Well, that means you're only looking at the car that's coming from the left. Where does it go to?
2.
It goes to 2. So the limit from the left would be 2. But the limit from the right is 1, right? So the limit at -1 does not exist, like we said, because the limit from the left is different from the limit on the right. See? So you're going to get some problems with those. So I think the graph ones are easier than the algebra ones, just because all you got to do is look at them and picture the cars. Do the cars meet? If they do, where do they meet? That's your answer. If they don't meet, does not exist. I mean, really, that's it. Okay? All right. So that's your homework for tomorrow.
So,
Yeah. I totally didn't.
Bad luck. I'm missing 2 pages out of this book.
Oh. And then they're kind of important ones, aren't they?
Yeah, kind of.
Well, I tell you what, let's just. I want to do that one.
just borrow another one for now and then bring it back when we're done.
Wait, I get to carry 2 books.
No, that's in the book. Yeah, in the book. I'm sorry, the 1 through 3 and 7 that you skipped, those are the ones in the book that you skipped, right? Do all the worksheet, right? Do all the ones in the worksheet. Geez, that'd be almost the whole worksheet. Yeah, that's what you was hoping.
Have you done Thursday or Friday?
Thursday and Friday.
Look at the website.
Yeah, video.